Hi everybody, this is Ben Herzog. I'm a meteorologist here with the National Weather Service, and if you're anywhere in southern Wisconsin, I'm sure you're well aware that it's an absolutely beautiful day outside. So with this relatively quiet weather we've got going on, we thought today it'd be a really good opportunity to explain to you how one of the most important tools in our tool belt works. It's something I'm sure you've all heard of, and I'm sure it's something you all have seen, and that's our weather radar. Because it's so important to us and we use it so much, and you guys see it so much, we thought you might like to learn a little bit more about exactly how it works. So we're going to go ahead and do this Facebook Live post, and now you'll have to bear with me. This is my first post on Facebook Live, so the potential for technical difficulties certainly exists, but I'll do my best to avoid that. I'm also going to do my best to try to pay attention to any comments or questions you guys might have and answer those as I can. So without further ado, let's go ahead and get started. So what we're looking at here are actually pictures of our radar here at the office. Off to the right there is that's the radar. It kind of looks like a giant golf ball on stilts. It stands pretty high up into the air, and it is up on a hill, so it can see quite a large area. What you're looking at on the left there is the satellite dish that basically sits inside of that dome and just spins around and around all day long. Radar is actually an acronym. It stands for Radio Detection and Ranging, and that's basically because that's how the radar works. It sends out pulses of radio frequency energy, and it bounces off of stuff, and it comes back to the radar. The radar we use now is actually based off of a prototype radar built way back in 1988, and so its technical name is the Weather Surveillance Radar 1988 Doppler, or WSR-88D. Now, explaining how the radar works is going to be a little bit easier if we can kind of put it in terms of what you might actually see out there. So what we're looking at here is a pretty typical thunderstorm. Now granted, this is out over the desert somewhere. It looks a little bit different than southern Wisconsin, but the concepts are still the same. You can pretty clearly see some clouds up here, and then below the clouds there's a very clear rain shaft. That's just very heavy rain coming down. On either side of the rain shaft, you can see it's clear, there's no precipitation, and then farther off here to the left, there's a little bit more rain. Now, let's imagine that there's a radar sitting off here in the distance, and it's sending its beam of energy out into the storm. Basically what happens, when its beam starts running into things, in this example, the rain, some of the energy gets reflected back towards the radar. And so where there's a lot of something out here, in this case there's a lot of rain, it reflects a lot more energy back to the radar. So that's why you get these warmer, more reflective colors. Where there's less precipitation or less things for that energy to hit, it reflects much less energy back towards the radar, and that's where you get the cooler colors. So here you can see there's nothing reflected back because there's nothing going on. There's more reflected back here where there's this heavy rain. Then the reflectivity decreases where there's less things to hit, and then it gets back into the rain and more energy is deflected back towards the radar. So what happens then is it goes from what you see in this screen to what you typically see on a radar screen, where you've got your radar centered down here, and as you go out, the beam eventually runs into some storms. Those reflect the energy from the original transmission out, and they reflect it back towards the radar. Highlighting this point a little bit more is here's another little schematic of how it works. Here's your radar sitting here, and what it does, it sends out this pulse of energy. It runs into the precipitation out here, and depending on how much precipitation is out here, that energy is reflected back. Going in on a much more fine scale where you can see the individual radar or the individual raindrops, you can see each one reflects back a little bit of energy. So it makes sense with the more drops you have, the more energy is going to be sent back towards the radar. And so when you get really high reflectivities, like in this example down here, that's when we can be confident that you've got at the very least heavy rain, if not some pretty large hail as well. So the one radar product I'm pretty confident you've all seen is something called reflectivity, and now hopefully you have a little bit better of an understanding of why it's called reflectivity, and that's because it's basically just reflecting back energy to the radar. So here's an example of a pretty strong thunderstorm that pushed through southern Wisconsin. I believe this was sometime last year, though I wouldn't swear to it, but you can see these very deep reds and oranges and yellows, and that's where the reflectivity is very high. That means a bunch of energy is being reflected back towards the radar, and that's where we've had very heavy rain, and where the reflectivity is very high here, I'd venture to guess there was probably some hail in that storm as well. A little bit more information on exactly how the radar operates. It basically starts at a low elevation and it spins in a circle, as you can see here. Once it completes one full revolution, it then notches up a little bit and it does another full revolution, looking a little bit higher into the sky. This keeps going on and on and on until really the lowest levels of the atmosphere are pretty well sampled, and we've got a very good idea of what is going on throughout the part of the atmosphere where a lot of the weather occurs. So that's pretty much all I've got for you guys. It looks like we've got at least one question in here. Somebody asked, to what height does this work and how many miles or feet? And that really kind of depends on there are different scanning strategies that the radar can go into, and so when we've got very severe thunderstorms, that's when we're going to be looking the highest into the storm. We could get up to, I would say, probably, I don't know, 40,000 feet, somewhere in that neighborhood. If we've got weaker storms going on, they're not going to reach as high up. Yeah, there we go. We've got some help from somebody at the office, says 40 to 60,000 feet. They've got the information right at their fingertips. When we got weaker storms, we've actually got some algorithms where the radar doesn't go up quite as high, and it basically just goes up to wherever the tops of the storms are at. No problem. So at this point, I don't see any other questions, so I'm going to go ahead and hang up the live broadcast now, but if you do have any more questions, feel free to mention them in the comments on this, and we'll get to them as we can over the next day or so. So thank you so much, and I hope you enjoyed my first Facebook Live post.